Okay, so we've talked about acids. What would you say, Fred? What do you think an acid is?
A compound that you put in water and the hydrogen ion results.
That's good. That's a good. I like that definition. You put it into water and the hydrogen ion results. Well, the hydrogen ion, if you think about water, and if I wanted to remove a hydrogen ion, what would I have left?
Um, Oxygen with a hydrogen.
That's right. I would have an oxygen with a hydrogen. The hydrogen ion has a positive charge because it just left. The proton just left by itself. It didn't take the electron with it. And so this ends up having a negative charge on it. Okay? So this is called what did we call that?
The proton.
What's another name for it?
Um, the hydrogen ion.
That's right. Hydrogen ion. So there's a couple names. And if you think of this in terms of how it interacts with water, it could be depicted like this, H3O plus, which we call the hydronium ion. Okay, so there's really three different names for this species. This thing over here, does that look familiar?
No, I've never seen that.
Here, let me rewrite it a different way.
Oh, that's the hydroxide ion.
That's right, it's the hydroxide ion. Okay, that's one of our polyatomic ions. The hydroxide ion is what's left over when a hydrogen ion leaves a water molecule, for example. Or you can say the water molecule is created when a hydrogen ion and a hydroxide ion come together. So the definition of an acid was a compound that when placed in water, the hydrogen ion results. The definition of a base is a compound that when placed in water, the hydroxide ion results. Some people simplify this to say an acid is a hydrogen donor, and a base is a hydroxide ion donor. It donates a hydroxide ion. That's fine. That's a fine perspective to have on it. Here's an example of a compound that behaves as a base, sodium hydroxide. You get the hydroxide ion because sodium hydroxide is soluble on our solubility rules. Group 1, sodium ions, sodium ionic compounds that contain sodium are soluble. Therefore, the sodium ion and the hydroxide ion result, and a compound that we put into solution and a hydroxide ion results is called a
base.
base. That's right, it's called a base. All right, magnesium hydroxide, put it into water. So we do have to look and see whether or not on this polyatomic ion chart if magnesium hydroxide is soluble first, right? This rule 6 talks about hydroxide salts. These are examples of hydroxide salts. Remember, a salt is just another name for an ionic compound in chemistry. It says most hydroxide salts are only slightly soluble. Hydroxide salts of group 1 elements are soluble. So hydroxide salts of group 2 elements are slightly soluble. However, or hydroxide salts of transition metal elements, aluminum, are insoluble. Thus, iron hydroxide, aluminum hydroxide, and cobalt hydroxide are not soluble. So hydroxide ion salts are only soluble if they're in group 1, or if they're group 2 elements, calcium, strontium, and barium. Okay? If they're transition metal or aluminum hydroxides, though those are not going to be soluble. Okay, so there's no list of strong bases on our periodic table, except for this tells us which ionic compounds are completely soluble that have hydroxide ions, and those are the strong bases. All right. Compounds can also behave like bases in this format. They go into solution. They don't have the hydroxide ion themselves, these weak bases we call them, but they pull a hydrogen from water molecules. And what does that result in?
The hydroxide ion.
That's right. If you pull water from a pull a hydrogen ion from a water molecule, the result is the hydroxide ion. Notice how there's this double arrow here. We didn't talk about that double arrow yet. Do you know what that double arrow means?
Does it mean it goes backwards too?
That's right. The reaction goes backwards. And that's a strong indicator, a sign, that this reaction, if we're talking about a reaction of a base producing the hydroxide ion, is the reaction of a weak base. That double arrow helps people recognize that it's a weak base. Only a relatively small percentage of the molecules or of this compound results in the products over here, or results in the hydroxide ion. Okay, so now we understand we've been introduced to acids and bases. We know that bases are compounds that release the hydroxide ion when dissolved in water. We have our strong acids that we've introduced. We have our strong bases that we can identify using the solubility rules.
How do you identify the strong bases again with the solubility rules?
So the solubility rule 6 here tells you which hydroxide salts, and those are the strong bases, hydroxide salts, the ones that are completely or that are soluble. And it says group 1s are soluble and 3 of the group 2s are soluble. So if you wanted to create a list, you would say it's lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, francium hydroxide. And then in group 2, it's just calcium, strontium, and barium. Calcium hydroxide, strontium hydroxide, and barium hydroxide would be our other 3 strong bases. And that's composed here, indicated here in our Rule 6. Okay, so that's how we identify whether they're strong or weak bases or acids. Strong or weak, acids or bases. So a little cartoon here. Here's HCl interacting with water molecules. This is a strong acid. How do we know it's a strong acid?
I'm not sure.
Because it's on the back of your periodic table, remember?
Oh, yeah, okay.
So let me bring up our strong acids here. HCl. HCl. We also knew because it said so right here, right? If it's strong, that means that when it interacts with water molecules, all of the water molecules remove the protons, and the result is a chloride, the same number of chloride ions as HCl's that I started with. The HCl completely dissociates, and all I have is chloride ions and acid molecules. Hydronium ions, hydrogen ions, right? Or protons. Either way, any of those 3 ways is fine to describe it. For a weak acid, we have a compound, some water molecules. There is some dissociation where a hydrogen comes off of the acetate ion here, and you get some acid. This, however, is not a complete dissociation because it's a weak acid.
What's wrong with the arrows?
What do you mean?
Why is it up above like that?
Oh, this one here?
Yeah.
Oh yeah, I got to move that back into there. Just a second. Is an indication that this reaction here of these acetate ions interacting with acid molecules or hydrogen ions pulls that hydrogen ion back off, results in the acetic acid, right? And hydrogen acetate and a water molecule. Okay? It's a weak acid. It's a weak acid. And only about 1 in every 10,000 acetic acid molecule will be dissociated at any given time. Okay?
How did you know that?
Well, it was it's just a rough number. We'll talk about it in general chemistry 2, how we can identify how much of those acids are actually dissociated. Okay? Oh, we call this equilibrium. This idea that these 2 reactions or these 2 compounds react to form these products, but then these products react backwards to form these products, right? Weak acids, what do you think? Do they create conductivity?
Weak acids or strong acids?
Well, either one.
Strong acids, yes.
Strong acids do. They completely dissociate. And weak acids?
No, they don't.
Well, we see a little bit of glow here, don't you? Can you see that?
Is that glow?
It is. It's glowing a little bit.
Well, because they dissociate a little bit.
That's right. Weak acids and weak bases dissociate a little bit. All right. Our strong acids, we have our list there. Okay. Some examples of strong bases. All right. Now, if we take a base and an acid, we can see that they will form products following this same pattern that we've talked about. A, B, C, D, forming A cation with a new anion, D, and C cation with a different anion. All right? This is a metathesis reaction, right? And you can see a base with an acid with a base. This is an example of a metathesis reaction. The magnesium ion goes with the chloride ion. The hydrogen ion here goes with the hydroxide ion. It's just that hydrogen hydroxide comes together as what we call water, right? Therefore, people will always say that when an acid and base react, the result is salt and water, salt water, right? And yeah, that's the case. Now, just in case you're feeling crazy and want to mix some acid and base and then say, oh, I can drink it, it's just salt water. You have to be sure that before that occurs, before anybody drinks the reaction of acid and base mixed together, that all of the acid and all of the base are completely consumed. If you have more acid or more base here, then obviously you'll have not just salt water, but you'll have salt water with whatever is left over. Okay, so we're going to look at a list of either acids or bases, and we want to kind of write how they behave, how they can actually be a base in solution or be an acid in solution. If it's a weak acid, we want to denote that it's a weak acid by writing a chemical equation that would show everybody it's a weak acid. Okay? So here's a compound. We're told that it's a weak base.
Methylamine.
Methylamine, good, CH3, NH2. If it's a weak base, do you remember how we said weak bases will act like how they can behave like a weak base?
I guess I don't really remember.
Remember we said that the base, if it's a weak base, has to have a water molecule to interact with.
Oh yeah, then it pulls away the proton.
That's right. It takes away a proton. And what's left over?
The hydroxide ion.
The hydroxide ion. So if we want to follow this weak base kind of pattern for methylamine, CH3NH2 would be our NH2 would be our weak base. So what's it going to do?
Take a proton from water?
That's right. It's going to interact with water and take a proton. So I'm going to write CH3NH3, and I have to make sure I put on a plus because it didn't take the electrons, it just took the proton. So it has that positive charge now. And then what's left over?
The hydroxide ion.
The hydroxide ion. Very good. So that's how methylamine will act like a base. Notice that we wanted to include the double arrows to help people recognize that this is a weak base and the reaction can go backwards. Okay. How about a weak acid? Nitrous acid, HNO2. If we didn't know this was a weak acid, we could have our strong acid chart and see that it's not one of them.
I think it is actually.
No, HNO3, nitric acid, but not nitrous acid.
Oh, okay.
Okay, so we have a weak acid, nitrous acid, HNO2. How is it going to behave in water then?
HNO2 just associates to hydrogen ion and what?
Nitrite ion.
Nitrite ion.
All right, HNO2 dissociates into, what'd you say?
Hydrogen ion and nitrite ion. NO2, is that just minus?
Yeah, NO2 minus.
Okay.
So, that's fine. I want to make sure I include the double arrows, right? Why?
Oh, it shows it's a weak acid.
Very good. Now, there's another way to write this, and we're often going to see this on exams and stuff, so I want you to become familiar with this way too. It's using the water molecule as kind of something to accept the hydrogen. So in that way, I would write this interacting with a water molecule. And I can write my double arrows again. What would my products be?
Oh, it goes with the hydrogen goes with the water molecule, so it's H3O plus
That's right. What do we call that thing? Do you remember?
hydronium ion.
That's right, the hydronium ion. And we still have the nitrite ion left over. Either of these is fine. Okay? Multiple choice in all of our quizzes and tests, so when it comes time down to it, you'll be able to recognize either one as the correct answer. Here's a strong acid, HClO4. Okay? What are the products if this strong acid ionizes in solution?
Um, hydrogen ion and is that the perchlorate ion, right? Yeah.
Yeah, hydrogen ion and the perchlorate ion. So HClO4 dissociating into,
Hydrogen ion and ClO4 minus.
okay, and what's the other way to write it?
With the water molecule
So HClO4 plus what?
plus water.
And then what are the products?
Double arrow.
Do I have to put a double arrow in?
Oh no, sorry, this is strong acid.
Okay, yeah, so if it's a strong acid, we don't put a double arrow in. And then HClO4, what are the products here?
Oh, H3O plus
3O plus and
ClO4 minus.
perchlorate ion. Okay, very good. How about this one? Strontium hydroxide. What are the products here for strontium hydroxide?
It's a strong base.
Strong base.
So I can't remember. How do you do this one?
Well, if it's a strong base, whoops, start over here. Strontium, SROH2. It told us it was a strong base, but we also could have used our solubility rules and looked at the hydroxides. Most hydroxide salts are soluble. Element 2 are slightly soluble. Hydroxide salt of group 2 elements, calcium, strontium, and barium, are slightly soluble. So they result in a strong base. Okay, strontium hydroxide here, acting as a base. We just have the hydroxide ion resulting, 2 hydroxide ions, and a strontium ion, 2 plus charge. Okay? Yeah, and that's that. We don't write this with a water molecule. You don't need to use the water molecule to write this. The order obviously doesn't matter. Strontium ion or 2 hydroxide, first or last here, doesn't matter. Okay, good stuff.